Hello everyone, I am Dr. Naresh Kumar, Assistant Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the question bank questions in network theorems and network topology. In this also we have total 20 questions in the network theorems and network topology. So first question, explain the steps in calculate Thevenin's voltage and state the application of Thevenin's theorem. So what are the applications? In the applications are analyzing the power systems. So for analyzing the power systems, we will use Thevenin's theorem, and in the Wheaton's bridge also, that single equivalence voltage, we will use this Thevenin's theorem. So first here Thevenin's theorem steps. What are the steps? Suppose I am taking one example. This one is the Thevenin's voltage. This is 100 ohms, 47, 82, and this is a 150, and this one is a 15 volts. Now here calculate the Thevenin's voltage means remove the load resistance from a given circuit and calculate the open circuit voltage. Remove the load resistance from a given circuit means where you want to find out the current means that is the load resistance. Remove that load resistance, calculate that. If it is a remove it, that means if you remove that one means that is open circuit, that calculate that open circuit voltage. That open circuit voltage is known as the Thevenin's voltage. That Thevenin's voltage, this is VTH, and you can substitute in the Thevenin's equivalent circuit, and this is the RTH, and this is the RL load resistance. Next, state the Thevenin's theorem statement and explain the steps to follow to determine the equivalent circuit while applying the Thevenin's theorem. So statement is number of voltage sources, current sources, and resistors are replaced by single equivalent circuit. That single equivalent circuit consists of one voltage source and one current, one resistor in series. So now reconnect the load resistance, that is RL. So this VTH and RTH can be calculated. So suppose same thing, same circuit I am taking here. So now 82, 47, 47, and this is 150, 150, and this one is 100, 15 volts. So to calculate this one, so remove the load resistance from a given circuit. Remove the load resistance from a given circuit first. V equivalent, and calculate this open circuit voltage, and this open circuit voltage is known as a Thevenin's voltage. And next for this one, remove the load resistance from a given circuit, short the voltage source and open the current source, and short the voltage source and open the current source, and calculate this R equivalent. That R equivalent is known as a RTH, 82, 47, and 150. So that 82 and 47 are connected in series, and 82 and 150 are connected in parallel, and 47 is connected in series. So now this is RTH, and reconnect the load resistance 100, and then calculate the current EC. Now here state and prove the Thevenin's theorem and explain with examples with DC circuits. So this question I explained in the Thevenin's theorem circuit. Thevenin's theorem in the second module I explained this one. Next, state and prove Thevenin's theorem with an examples. This one same question here. State and verify maximum power transfer theorem with an example for DC excitation. So this one is also explained. So you can go through that maximum power transfer theorem in the derivation. So when load resistance equals to source resistance, then maximum power transfer to the load. So this is the RS, and this one is the VS, and this one is the load resistance. So this is variable. When RS equals to RL, then here is the P maximum, power maximum. So that maximum power equals to Vs square by 4 RL. This derivation I explained when load resistance equals to source resistance. Just watch that lecture, then you will get that one. Next, sixth question. Explain the Thevenin's equivalent circuit with their importance. So Thevenin's equivalent circuit, this one RTH, and this one is VTH, and this one is a RL. This is Thevenin's equivalent circuit, single equivalent circuit, voltage source in series with resistance. Any circuit, any complex circuit, we can simplify as a Thevenin's equivalent circuit. Then we can calculate the current flowing through the any resistor current in any complex network. So what is the importance here? We can analyze the power systems, uh, power system network, power system circuit, and we will use that Thevenin's theorem. So for determining the voltage source value in the Wheaton's bridge circuit. Next, so define the graph. Any circuit, we can replace it by lines. That voltage source is replaced by short circuit and current source is replaced by open circuit, and all elements resistor, inductor, and capacitor are replaced by circuit. Such graphical representation of circuit is known as a graph. If that graph knows the directions, that is oriented graph, or undirected graph, directed graph. If directions are not unknown, means that is the undirected graph, means non-oriented graph, unoriented graph. Planar graph and non-planar graph also we discussed in the previous lectures. So planar and non-planar. Next, explain the formation of incidence matrix. So this we already discussed for this circuit. So incidence matrix can be drawn. So number of nodes cross number of branches. If branch is entering towards the node, take a negative sign, and if it is leaving away from the node, take positive sign. If it is not associated with the branch, that is zero value. So these elements are 0, 1 and -1 only. So now with suitable examples here, this one is also I explained. So you can just watch that incident matrix lecture. So demonstrate the formation of matrix using tie sets for determination of links and branch currents. Link currents and branch currents here. So now here, this is the tie set matrix. Tie set matrix here, A. So number of loops cross number of branches here. A, B. Suppose this is the branch network. So now here possible number of loops here. This one link currents. This is the tree. So these are the links. So now here A, B. Let me change the color over here. A, B, C, D, E, F. So this one, and this one, F, D, E, and F, D, E, and A, B, C. A, B, C are the twigs, and F, D, D, E, F are links. So now here the link currents we can calculate here. So now here this one is the loop currents I1, I2 and I3. These are the link currents. So from this you can there is a determination of link currents and branch currents. So this one. Next, define the graph. So graph definition: graphical representation of electrical circuit. Tree means without closed path. It should consist of all nodes. And co-tree means, so if it is this one, this is the tree. So this is the graph, means here. If it is this one is tree, means the remaining part of the graph is known as a co-tree. And next, branches are the element which is having two terminals, and links means these are the links. This is one link, and this one is one link, and this one is a link. And node means two or more branches connected to one point. So here this is one branch, this is one branch, this is one node, this is one node, this one is one node, and this one is one node. And degree of node means number of elements connected to a node. This A node degree of node is 3, and B node degree of node is 3, and C node degree of node is 3, and next this node is also 3 degree of node. Next, take any graph and draw the all possible trees and basic tie sets and basic cursors. So if suppose this one is I am taking, so now for this case possible number of trees. So for this one, This is one tree. It should consist of all nodes and without any A, B, C. And next, this one, this one, and next this one, next this one, this one, and next this one, this one, this one. So all these are trees which are having all nodes without any closed path. So for this we can determine basic tie sets and basic cut sets. Determine the branch currents and link currents using tie set matrix with n examples. So this one is also explained in the previous lecture. Determine the branch voltages, and this is using cut set. In the cut set also I explained twig voltages and twig uh, matrix in the previous lecture. So state and prove the maximum power transfer theorem. The following: when load resistance equals to source resistance. So this one is also explained. So Vs, and this is the Rs. This one is the load resistance is variable. When load resistance, when RL equals to Rs, then here P is the maximum value. When load resistance equals to source resistance, then maximum power transfer to the load, that maximum power equals Vs square by 4 RL. This is the formula. So now here from this is the IL equals to Vs by Rs plus RL. So power equals to power across the load equals PL equals to Vs I square IL square RL, that equals Vs square by Rs plus RL whole square. So now derive with respect to the RL, and PL derive and with respect to the DRL equals to 0. If you do that, you will get the RL equals to Rs, load resistance equals to source resistance. If substitute in this, and you will get this value. And next question, the graph of network has 5 nodes and 9 edges. So B minus L plus 1. L equals B minus N plus equals to 1. So number of branches and number of nodes, and this one number of links here. So now here, so 5 minus, so 9 minus 5 plus 1, that equals to, this value equals to 4 plus 1, that equals to 5. Next question. Describe the Norton's equivalent circuit with their importance. So what are the importance? Same thing, same importance for Norton's equivalent circuit and Thevenin's equivalent circuit, both are same. But here this one is current source in parallel with the resistance. So Rn and In, this one is also same. Determining the analyzing the power systems, and next here in different types of, wherever we use Thevenin's equivalent circuit, where single current source is required and single resistance is required, there we will use this Thevenin Norton's equivalent circuit. And next, mention and prove the reciprocity theorem for a given DC excitation system. This one, it can be applicable only for single source network, not for multi source network, and it can be only applicable for linear bilateral network. So linear and bilateral network. So this is the circuit, and this is the response, and this one is the excitation. And next, this is the linear bilateral network, and if you interchange the source and this source E1, and this is the excitation, the ratio of response to the excitation is same, I dash, E dash, E dash. The ratio of response to the excitation is same when you interchange the source terminal and branch terminal. So that is also explained in the reciprocity theorem lecture. Just watch that lecture. Mention and verify Thevenin's theorem with an example for DC excitation. So verify the Thevenin's theorem means this one. This one is RL, RS, RTH and VTH. So total 7 to 8 problems I considered in the previous lecture. In that I verified. So take one example. So these examples, so 82, 150 and 47, this is the 100 and this is 15 volts. So for this circuit I verified is a 48 milliamps here, and this one is also Thevenin's 9.6 volt and this is 100 and this one is 100. Here also 48 point. In our laboratory circuits you can use that circuit and you can verify that. Next, mention and verify Norton's theorem. Same thing here, that current source in parallel with resistance RN. So here 96.5 and this is 100 and this one is the 100. So same circuit, 82, 47 and 150. This is 100 and this is the 15 volts. So for this circuit, same 48 milliamps. This is our laboratory circuit and this is the 48 milliamps. If you connect 1 ammeter, this one. So you can calculate from the Thevenin Norton's equivalent steps also, this one. And next, 19th question, mention and verify maximum. This circuit, you take this one. So this question, 40, this is 1000 ohms, and here 5 volts. And this is change. This is our laboratory values 47, 82, 100, 150, 220 and 470, and next 1000 and 2000, 220. Verify the maximum power transfer theorem means just how you will verify this one with a suitable example. Just calculate the current here. So I square R. So I square R means you will get the power. So here P should be maximum at this condition. So this value equals to P maximum equals to Vs square by 4 RL. So this formula is important. And next, so total 20 questions we discussed. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you very much to you.
Like, share and subscribe. Hit the bell icon for more updates.